Test, test. Microphone, yep. Okay. Can y'all hear me okay at home?
Yes.
And I'm about to share my screen, yes?
Yes.
All right. All righty. So I provided everybody via email a summary of the volume, solids of revolution. And if you came to class today, which I do have some students here, I have provided you a color copy of these notes. All right, you got one there? Grab one off the desk there. So we're going to do some more. We're going to do some more solids of revolution today, and I want to really make sure that you're clear on this idea. And in the email, what I said is I dug this up out of an old file, and then I realized that the notation that I used here is slightly different than the notation I used in class. So we will discuss that when we get to it. On top of that, last night I sat there and watched some baseball, and while I was doing it, I decided to start from scratch and code up something new to demonstrate the difference between the two methods that we have for finding volumes, washers and shells. And I think if I show you this animation, hopefully you'll be able to see the big difference between the two. And that should help us with this, this sheet. Okay, so let me bring that up first. Where is it? Here we go. What is going on here? Trying to find it. There it is. All right, let's start this thing out. For those computer science majors, I left my code up here so you can see it there. It is fun stuff. I did. Yeah, it's not as bad as it looks. It's not as bad as it looks. A lot of it is built-in functions. You just know, really the hardest part is using the functions to graph what I need it to graph, which means I used a ton of Cal 3 to do it, because in Cal 3, we learn how to draw things in three-dimensional space. You have to know how to do that to get it to do what it's about to do. So here we go. So we have two functions, right? A red function and a blue function. The red function is a function of x, right? You draw vertical lines, it passes the vertical line test. The blue function is a function of x. The blue and the red are not functions of y though, right? Because horizontal line test will fail. So if I'm going to do any rectangles in here, they have to be vertical rectangles. Do you all understand that? Because horizontals won't make any sense because they're not functions of x. So once I have this rectangle in here, I can kind of imagine moving that, well, yeah, moving that rectangle, you know, all throughout that region. And if we're trying to find the area, right, it's just adding up all those rectangles. But now what we're going to do for a volume is we're going to try and revolve this around the x-axis. Now, I know I showed you this last time already, but I'm going to be able to show you both of them simultaneously, the washer and the shell. So you'll be able to see the difference. So I'm going to take this and let me move it over to the right. No, I'll leave it there. And I'm going to wrap that thing around the x-axis. So here it goes. It gets wrapped around. And when I do that, I get this shell, right? Nice shell here. I mean, sorry, washer. And then what I'm going to do is find a formula for the volume of that one washer. That'll be the integrand. And then I'll add them all up. So I'll start here at the left. And then I'll have that, you know, all the washers starting from A all the way over until I get to the other side. And that's B, right? And I want to add all those up. If I do that, add all those up, I'm going to get this thing. Going to get a solid. You all see that? This is some solid. And you can see the washer within that solid, right? It's just all those washers put together creates that solid. And so that is the solid object we get when we take that region bounded by those two functions and rotate it about the x-axis. That's the washer method. I told y'all last time, when you're doing washers, your rectangles would be perpendicular to your axis of rotation. Now, in your notes, I don't use the word perpendicular. If you look at the very top of this, method of washers, I say method of washers. Rectangle is orthogonal to the axis of rotation. Orthogonal means perpendicular, okay? So just a little definition there for you, all right? So anytime your rectangle that you want to swing around is perpendicular to the axis of rotation, you know you're using washers. All right, now let's compare that to this. Let's take that same region, okay, that same rectangle, but this time let's wrap it around the y-axis. So if I take that one little sliver and wrap that around the y-axis, it's going to look like this. You got to bring that sliver all the way around. Let me look at it kind of from the top. Do y'all see that? I mean, there's a major difference between wrapping around the x-axis and wrapping around the y-axis, right? So you should get a different volume if you do this, yeah? Now, if I take all of those shells, that's what this is called, a shell. So washer looks like a washer, shell looks like this. If I were to just start at A, right? So start here at the left side, have that shell, and then do all the shells, all these shells together, put them all together, then I should have something that looks like this. Can you all see that? Almost looks like kind of like a donut or something.
So does a shell only apply to vertical reflections?
So when we use shells I'm not sure if this is going to answer your question. A shell is when your rectangle you have is going to be parallel to the axis of rotation. So because the y-axis is parallel to that rectangle, we're wrapping it around this way. That's a shell. All right. If we go the other way, this way, right, perpendicular, then you have a washer. I don't know if that answered your question.
Yes.
Okay. So I'll put the other one up here just so you can see it. So this one right here was what we got when we wrapped that region around the x-axis. This is what we got when we wrapped that region around the y-axis. Obvious that these are going to have different volumes, right? Okay. So really, you're just looking at whatever problem you have, you're going to do what you're told, right? If it says wrap it around this axis, then you're going to, whatever axis it is, that'll determine the washer or the shell method. So on the notes here, are there any questions? On the notes here, when you look at method of washers, do y'all see that I have one drawing here, which is basically the drawing that we just had? We have a function on top, a function on the bottom. We're going to take that, we're going to rotate that around some axis, and it's going to create this washer. And what we're most interested in is the outer radius and the inner radius. The outer radius, which I notated R sub 0 here in class. Last time I didn't use that notation. R sub 0 or R sub O, radius out, okay? Radius in, R sub I. Those two are always, and this is what you were asking yesterday or the other day, Bree, what is the outside radius? And I said, the outside radius is the distance from the axis of rotation to the outer edge of the rectangle. The inner radius is the distance from the axis of rotation to the inner edge of the rectangle. So in the animation that I did right here, what I'm going to go home and do, and y'all won't be able to see this semester, but I'm going to redo this. I'm going to mess with this so that I can have my axis of rotation be anywhere instead of, right now, this only works for x-axis and y-axis. But I want to be able to do it for any, because I want to be able to show you the difference between rotating this region around the x-axis versus some line that's above it or a line that's below it. That's going to be much harder to do, but that's for fun. You could shift it, yeah, but I want to make the graph still have the x and y axis in the same place, right? I don't want to move the whole function region down. I feel like that's cheating. So it can be done. It's just gonna be a little harder. Okay, so here's the formula for it, right? It's the outer radius squared minus inner radius squared. That's basically the difference of the radii. And then dx is the thickness of the washer. And then the pi, because pi r squared is the formula we had, integral a to b, that's your volume. Okay, again, the rectangle was perpendicular to the axis of rotation here. Now, below this, I change everything around. Instead of having functions of x, we have functions of y. So notice that the blue and the green are functions y, but not x. They fail the vertical line test, they pass the horizontal line test. If we ever have something like this, then your rectangle has to be horizontal, can't be vertical. And if it's horizontal, and I ask you to wrap it around the y-axis, then you're going to have to use a washer, right? Because it's perpendicular. So to do that washer, it's the same formula. You need an outer radius and an inner radius. The difference is that these are all going to be functions of y instead of functions of x. And then your limits of integration are not a and b, it's c and d, which is your upper and lower limits here. Okay. So that's the way it works for washers. You either have a vertical rectangle and you're going around this way, or you have a horizontal rectangle and you're going around this way. Now, the shells method, which is the next page, the shells method is when your rectangle is parallel to the axis of rotation. So we go back to the two scenarios again. What if we have a function of x, two functions of x, and we want to wrap, then we have to use a vertical rectangle. We have to. And that means if we want to go around the y-axis or something parallel to the y-axis, we want to go this way, we have to use shell method, right? You have to. And so the shell method, I derived that in class last time. I won't go through all of this again, but basically it's just 2 pi integral a to b. Now this right here was the critical part. I used r sub x in class last time, but this capital R is the way I notated it here, is the distance from the axis of rotation to the rectangle. So I have it notated here. I told you that the distance from the y-axis to the rectangle is x, that's this, that'll always be x. And then the distance from the axis of rotation to the rectangle will always be capital R. So depending on where that line is, that will dictate what capital R is. And we'll do some examples, but there's our formula. 2 pi integral a to b, capital R, I like to say the top function minus the bottom function. That's basically what that is. Okay, so that's if we have functions of x. What if we have functions of y? Well, if we have functions of y, then our rectangle has to be horizontal. And that means if you're going to do a shell, it's got to come this way. And so that would be how you do it if you have an axis of rotation that is horizontal. Now these are parallel to one another, and you rotate this way. And the formula is exactly the same. You have 2 pi, integral goes from c to d instead of a to b. And then r is the distance from the axis of rotation to the rectangle. So from here to here. And this distance from here to here is y now, not x. And then this right here is your difference between your f and g. The f function is the right function. The g function is the one on the left. So there are 4 scenarios. Okay, that's it. There are 4 scenarios. If I give you a region and I ask you to wrap it around things, the first thing you want to do is determine, are these functions of x or functions of y? If they're functions of x and you want to go this way, washer. This way, shell. If they're functions of y, you want to go this way, shell. This way, washer. It makes sense? That's it. Those are the only 4 things that could happen. Okay, so let's do an example. Yeah. We'll do an easy one first. I know we did this last time, but I really want to make sure you understand this, all right? Because this is going to be a pretty significant part of your test. All right, so let's do an example. We'll start easy. Let's go with these functions or these equations. Let's say x is equal to y squared and x is equal to the square root of y. And I want us to find the region bounded by these curves. And okay. Well, let me do this. And then find volume if region is rotated about, and now I'm going to give you a bunch of scenarios. So here's the first thing I want. I want us to rotate it about the x-axis. Then I want to rotate it around y equals -4. Then I want to rotate around y equals 3. Then I want to rotate it around the y-axis. Then I want to rotate it around x equals 5. And then the last one, x equals -7. That's pretty much like what something on the test would look like. I give you a region, then I ask you to wrap it around 6 different lines. And I will not ask you to evaluate these, okay? We're not going to get the answer. All we're going to do is set up the integrals here. All right, so what is the most important part of this? The draw. You got to draw this correctly, all right? So this might be a good time. Well, no, not right now. We're not going to do it right now. Okay, so here we go. I'm going to go and try and graph this. And maybe I'll take a little bit of time to make sure I get it right. So we have x equals y squared. That'll be the blue one. The other one is x is the square root of y. So what does x equals y squared look like? Parabola opens up to the right, right? It's a parabola that opens sideways. So in the blue one, it'll look like this. Start out at 0, 0. It'll go up through there. That's the point 1, 1. And then at 2, it's at 4. So, or yeah, like that. And then on the other side, it does basically the same thing. Okay. And then x is the square root of y. So if you're unsure, I think I showed you this before. If you're unsure what this looks like, you can make a t-table with x and y values here. So if you plug in 0 for y, but because it's a function of y, right? These are functions of y because they're solved for x. You're going to start by plugging y values in. So if y is 0, x is 0. If y is 1, what's x? If y is, let's not do 2 because we have to take square root of it, right? Maybe 4. 4, then that's 2. I can just plot these points 0, 0, 1, 1. Make sure we do this right. 2, 4, which would be somewhere over here. And I think that's enough for us to see that we've got this happening. Is that all right, everyone? Do y'all see the region bounded by the 2? There? It's the region bounded by those 2. I'm going to take that region. I'm going to wrap it around the x-axis, the y-axis, or all those different axes, right? All right, now my picture, now that I have it drawn, I'm going to redraw it to make it bigger so I can kind of like see everything, all right? So I'm going to redraw this picture because it really only exists in the first quadrant. And it goes something like this. It goes like this. And then the other one goes something like this. Right? And what was part A? To wrap it where? X-axis. All right, so I want to go around the x-axis. All right, so if I want to go around the x-axis, I look at these and I ask myself, are these functions of x or y? just looking at them. They are functions of y, but are they functions of x also? They are functions of x also. Right now, this blue one goes to the other side though, right? So that wouldn't be. But you could just cut this side off and look at it as functions of x. But because it was given to us as functions of y, I'm going to stick with that, okay? So I'm going to write down the equations here. The blue one was x equals y squared. The red one was x equals square root of y. I'm going to rewrite those as functions. I'm going to call the red one f of y equals square root of y. And then the blue one, I'm going to call it g of y, and I'm going to call that y squared. Now, the red one I called f only because it's the one to the right. But it doesn't matter. As long as you know what the right one is, you don't have to do f and g. F doesn't have to be the right one. It's just to follow the formula that I gave you, I'm going to make the red one f. All right, so because I'm looking at these as functions of y, I'm going to have what rectangles? Vertical or horizontal? Horizontal, right? So I got this horizontal rectangle in here like this. And I want to wrap that around the x-axis. So here's my axis of rotation. I'll do it in highlighted so it's a little easier to see. My axis of rotation is here, right? Which is actually the x-axis, right? So what method am I going to use? Shells, okay? I've got to use a shell. I'm going to use shells, and the reason I'm using shells is because the rectangle is parallel to the axis of rotation, okay? So the shells formula says this. Well, if you go to your formula sheet, right, we are looking at shells, and we're looking at the bottom one, aren't we? Because that's the one we use when we have functions of y. So that formula right here is what we're using, right? This formula, copy it here, let me throw it in here. I need to know f of y, which I have, right? I need to know g of y, which I have. By the way, I noticed after I printed this, I'm missing a parenthesis on that formula sheet. On right here, there should be a parenthesis right there. Right after that g of y, there should be another parenthesis. So technically it's wrong, but it's a little typo. Okay, so I know this is the function that's on the right side. This is the one that's on the left. And then let's get C and D. Do we know C and D? Those are going to be y values, right? Not x values. So 0 here and 1 here. Now, if you didn't know that, you could set the two equal to each other, right? We could set to find the intersection. It's always good if you can visually do it. But if you needed to, you would do this. You would square both sides. You would move the y over. You would factor a y out. You'd set those both to 0, and you get 0 and 1. That's the algebra that would have been required. Okay, so we got 0 and 1. That's our C and D. So really the biggest thing here for us to figure out is R. And R is, according to the formula sheet, R is the distance from the axis of rotation to the rectangle itself. And wait, back to this, sorry. Here's Y in this, here's R in this, right? It's the distance from the axis of rotation to the rectangle vertically, this way, up and down. And we also have to know that the distance from the x-axis to the rectangle is always Y, always, which is going to be what R is here. Because when we look at this rectangle, if we ask ourselves, what is the distance from the axis of rotation to the rectangle? Well, it's also the distance from the x-axis to the rectangle, which is Y. So I think we have everything to set up the integral. It's going to be volume is 2 pi integral 0 to 1 r, which is y, and then the function to the right, which is square root of y, minus the function on the left side, which is y squared dy. And that's it. We could evaluate that integral. This integral wouldn't be bad at all because we could just distribute y through. And then we would just have a polynomial, just not a polynomial, sorry. We would have y with various powers, and we just do power rule on each one, and then we'd be good. So that's what I would be looking for on the test. This integral set up properly like this. Is that okay? Okay. 1 down, 5 to go. So on the next one, I'm basically going to have the same picture drawn, except a different axis of rotation. So I'm going to go ahead and do that. No questions yet? Is this making more sense than last time? Or is it just about the same? A little bit better? Same for you? All right, so here we go. We got this. All right, we already know that we have to have our rectangle go this way. For part B, where do I want you to rotate? Y was -4. Okay, so now my axis of rotation is going to be down here. Right? This is not drawn to scale. This is -4 down here, right? -4 down here. This is my axis of rotation. So we should still have that same formula, shouldn't we? The only thing that's going to change is what? R. It's the only thing that changes. We still have the function on the right. We still have the function on the left. It's just the distance from the axis of rotation to the rectangle. This distance, R, is not y, right? The distance from here to here is y. And so if I want this total distance, I need to also know this distance, which we know is what? 4. And we will look at it like an absolute value, like a distance. So we're going to put 4 here. So R is y plus 4. And that's it. Everything else is the same. Square root of y minus y squared dy. Oh, I should have stated shells again, right? I'm doing shells because my rectangle is parallel to my axis of rotation. Any questions there? Okay. You sure? All right, next one. We'll start going a little bit quicker here. The next one, maybe I won't draw it so big this time. Got my region here. It goes like this. Well, it's getting sloppy. It goes like this. I'm still going to use my horizontal rectangle. This time for part B, where's my, C, where's my axis of rotation? Y equals 3, which is above it, right? Y equals 3. So my axis of rotation is up here. So everything else is still the same, right? We just have, all we have to do is figure out what that y is. I mean, sorry, what that r is. So I'm still doing shells. The distance, okay, r is the distance. If you were standing here, it would be the distance from the axis of rotation to the rectangle. That's r. We know the distance from the x-axis to the rectangle is y, because it always will be y. And then we also know the distance from here to here is, oh no, not there to there, all the way down to the x-axis, right? Here to here is 3, right? So what would r be? 3 take away y, right? Not y take away 3. 3 take away y. So we got it. Volume will be 2 pi, integral 0 to 1. 3 take away y, square root y minus y squared dy. Is this better than trig sub? Got a question?
So wouldn't
Well, no, because we're always looking left to right. When our rectangle is horizontal, we're not looking this way, we're looking this way. And this one is still on the right side, this one's still on the left. I know what you're saying. It's like, because we're on the other side, does that now change these? But it doesn't, because we're only concerned about the left and right of them. If it was perpendicular, it would, but it actually turns out to not matter. And the reason is because when we do that, it'll be a washer. And in the formula for washers, we square. And so really, when you square it, it doesn't matter what order it's in. Think about the, well, I'll put it on here. Think about if I write 3 minus 4, right? That's -1. If I do 4 minus 3, that's 1. But if I square these, I get the same answer. So when that situation comes out, what you're talking about, with the washer formula, we're going to square, so it won't matter. Good question, though. Good question. Yep. Okay. That's it. First 3 down, 3 to go, right? So now we're going to do part D. So for part D, what are we going around on D? Y-axis. Okay. So we're going to draw the same region. I'm still going to use a horizontal rectangle. But this time I want to rotate around the y-axis, which is here. And now I'm going to have to use washers. Right? Washers. Because my rectangle is perpendicular or orthogonal to the y-axis. So on our formula sheets that I gave you, it's which one? If you look at these, there's 4 red boxes on this thing. It's the second one. Okay, it's the second one here. It's a washer with our functions being functions of y. So I'm going to go to that right now. It is washers, second formula here. So we need C and D. We have C and D, right? That's still the same, 0 and 1. We still have those. 1 here and then 0 here. So we got that. We need the outer radius and the inner radius. So this is where I told you last time, what I like to do is I like to kind of like take this y-axis, move it down, draw your rectangle. The red curve is the right side. The blue curve is the left side. Draw your axis of rotation. There it is. And then label your R out and R in. So the distance from here to here is R out. The distance from here to here is R in. And now we just need to figure out what they are. Well, R out is the distance from the y-axis to the red, which is the red function itself, right? As a function of y. And what is that function? That's square root of y. And then the Rn is the distance from the y-axis to the blue function, which is the blue curve itself, which is y squared. Understand? And so now we have everything we need. The volume will be not 2 pi, that's shells. Pi, integral 0 to 1, outer function squared, square root of y squared minus inner function squared, y squared squared, all of that dy. And of course, when you square it, that'll be easy to do. But that's all we need for this. What do you think about that? So you do like this better than partial fraction decomposition? Yeah. Yeah. All right. Next one. You're waiting, right? You're like, when's the shoe gonna drop? Okay, so the red one's here, the blue one's here. Horizontal rectangle. Okay, for what are we on, DE? On E, what do we have? X is 5. Okay, X is 5 is over here somewhere, right? And so our axis of rotation is way over here. And so when I go to label things, if I were to do what I've been doing with those drawings, I draw the y-axis here, my axis of rotation here, my rectangle here, with the red one here and the blue one here. This little drawing I'm doing is just kind of like, if this gets too cluttered when you do a drawing and there's too much shit in here and it's confusing you, by just kind of moving the important information down here, it's easier, I think, to see what R out and R in is. So R out is the distance from the axis of rotation, that's over here, to the outer edge of the rectangle, which would be the blue, wouldn't it? So that would be from here to here. Whoa. From here to here is R out. And from here to here is R in. What we do know is that the distance from here to here to the blue, that's y squared. And the distance from here to here is square root of y, right? There's one more distance that we know that's going to be important here, and that is the distance from here all the way across, which is 5. So let's start with R out. What is that distance? It's this whole distance, right? 5, but take out this much of it, right? So 5 minus y squared. Take the whole 5, but then take out just this piece, and you'll have that piece. So R out is 5 minus y squared. And then what would R in be? 5 minus, so this piece here is the whole 5, right? But take away that red piece. So 5 minus root y. And that's all we need for the formula. Everything else, just plug and chug. So the volume should be pi, because we're doing a washer, 0 to 1. Outer radius squared. So I'm going to put 5 minus y squared, and then what? Minus, plus, what do we do here? Minus, and then 5 minus root y, that squared. Okay, there it is. Questions? One more. One more. So for the last one, we had, what are we on? E? C, F? Yeah. What was the last one for F? X is -7? Okay, so my graph's going to look like this. Blue one, red one. We've done this so much already. Here's our horizontal. Axis of rotation is way over here at -7. I'm going to draw everything again. Y-axis, rectangle. Red one, blue one. Axis of rotation over here. R out is the distance from the axis of rotation all the way to the outer edge of the rectangle, which is the red one. And then the Rn is the distance from here to here. Can someone tell me what R out is? 7 plus square root of y, and then Rn is, oh, what's going on here? Rn is what? 7 plus y squared. So we know from here to here is y squared. We know from here to here is root y. And we know that from here to here is 7, right? So all we had to do is take the 7 and then add the y squared. That gave us the inner one. And take the 7 and add the root y, and that would give us the outer one. We're done. Volume equals pi integral 0 to 1, outer 1 squared, 7 plus root y in parentheses squared minus inner 1 squared, 7 plus y squared squared dy. We're done.
For the integral, like what we're doing, like how would it change if we were looking at
It is possible that if we were to have looked at these as functions of x instead of y, it could, you know what? No, they still, on this one, they still hit each other at 1, 1. But it could be that they don't, right? So that's a good question. If you change it from, if what I give you can be looked at both ways, your limits of integration on the x might be different than your limits of integration on the y. Okay, so I was up very late last night. I was laying down trying to fall asleep. I was tossing turning, I don't know why. And I was trying to think of what function I wanted to give you to do this next one. All right. So I thought of this. I haven't even looked at it. Let's just see what happens here. Okay. So what I'd like for us to do is consider this, the region bounded by, here's the function or equation, y equals x square root of sine x, y equals 0, x equals pi. I've given you 3 different curves, and I want you to see what the region bounded by those 3 are. Now, we probably don't know what x square root of sine x looks like. So you're probably going to need your graphing calculator for this. All right. I'm going to use Desmos to graph. Now, I'm assuming here that everybody knows how to graph something on their calculator. A function of x. No? No? Really? You don't know? Okay. It's okay if you don't. So you just have that. I always make fun of people who have that real fancy calculator. It's just like desk eye candy, right? Just to look at and don't know how to use it. Yeah. Learning how to use those things is a tall task, right? So let's see. To do this, you're going to go. I know some of you know how to do this, so I'm just going to help people who don't. Okay. So you two. So go to. Do you know how to do it? Yeah. Okay. Let me see. Okay. Go to y equals top left. Y equals. There you go. And then you're just going to put in x. You should have an x variable there, which is right there, that key next to the green one. See where it says xt theta n? Right there. Hit that. And then times. And then you know how to do square root? Square root. And then sine. Your sine is right there. And then, oops. Yeah, sine, just hit it. And then x. And then that's it, close parentheses on that x, then hit graph. All right, now when you graph this, you need to make sure that you are in radian mode. Radian mode. If you're in degree mode, things are going to be different. Bree, did you get it? It's going to be a weird graph. I'll bring up the graph here. I haven't even done it myself yet. Come on. X times X times the square root, no, I need to hit SQRT of sine X. There we go. It should be a really weird looking graph. All right. Anyone else need help on the graph? Got it? You got the graph? You sure? All right, we're looking between, okay, so there's the graph, right? I'm going to copy this graph. Okay, there's my graph. Okay, that is y equals x sine x, right? That is not a region yet. Okay, that's not a region, that's just a curve. Now, I also put here y equals 0. Y equals 0 is the x-axis. Now we have a region. And you know what? If I just would have thought about it for a second, I'd realize I didn't need x equals pi. Because x equals pi is a vertical line. And I don't need it because it actually closes off there. I was afraid it didn't. I didn't think too deeply about it. Obviously, sine of pi is 0. So, okay. There's our region. You got it? Now, if I asked you to wrap this around 6 axes, just like the previous problem, right? You can do that, yes? Now, in terms of the rectangle that you want to use, what type of rectangle are we going to use here? Vertical or horizontal? Vertical, right? Because this is definitely a function of x. And so my rectangle on the inside would go like this. And that means if I want to wrap it around the x-axis or any line that is parallel to the x-axis, I'm going to have to use what method? Washers. And if I wrap around the y-axis or any line parallel to the y-axis, I'm going to have to use shells. Understand? Okay, I don't want to do 6 problems right now. I want to do one, and I want to take it the entire way to an answer. All right? So let's just do this around the x-axis. Okay? About the x-axis. So I want to find the volume if rotated about the x-axis. Y'all doing all right at home?
Yeah.
Yeah. Were y'all able to graph it at home? For those of you who have a graphing calculator, were you able to get that?
Yes.
Yep.
Okay. All right, so we're going to rotate about the x-axis. Here we go. I'm going to redraw it just real quick. I have this general picture. It's like this, comes back down. Got my rectangle in here. I'm going to rotate it about the x-axis. So I'm going to do washers. And in terms of this formula sheet I gave you, the 4 boxes, this will be the first one, right? We're going to do that first box on this formula sheet. So I'm going to draw my axis to the right side. Here's my x-axis. This is also my axis of rotation. I'm going to draw my rectangle. My rectangle always touches the x-axis, doesn't it? And the red curve dictates the top, but the bottom is always just 0, isn't it? Okay. The outer radius, right? Isn't that what I need? Do I need to put should I put the formula? I have it. I may as well go grab it. Doesn't take that much to go grab this. So I need the the outer radius and the inner radius. So the outer radius, distance from axis of rotation to the outer edge, isn't that just the red function? So that's just x square root sine x. And then the inner radius, what's the inner radius? Well, it's always on the ground, right? So the inner radius is always 0, right? Y equals 0. Yeah, okay. How about A to B? We need where we start and end. 0 to pi. And that was kind of given by the picture. So 0 to pi. So my volume will be pi integral 0 to pi of the outer radius, which is x square root of sine x squared minus 0 squared. Yes, that's correct. Dx. Yes, Cruz, you said that correctly. There's our integral. I'm out of room on this page. Can I move on to the next page? Let's go ahead and square things. So this becomes pi integral 0 to pi. And then when you square that, you have to square both the x and the square root of sine. So when you square x, you get x squared. When you square the square root of sine, you get sine x. And then the 0 is not there. So there it is. And I want to take this all the way. So Cruz, I heard you said integration by parts. That's correct. I'm going to look at this integral by itself over here. I'm going to do the indefinite integral, get the answer, then I'm going to come back over here and do the definite integral. So if we do integration by parts, what's our u and dv going to be? U is x squared, good. dv will be the sine x dx. Du will be 2x dx, and v will be negative cosine of x. So now we do ultraviolet minus voodoo. So this integral turns into ultraviolet, which is negative x squared cosine x, minus, okay, now voodoo, which is this times this. I'll have a negative and a 2 that can come out. So in the formula, it's a minus, right? But I'm going to change it to a plus 2. Then the integral that's left, which is only an x cosine x dx. Now we have to do it again, right? Do integration by parts one more time. I'm going to give you all a real big hint. There's something like this on the final, all right? Guaranteed. It's even going to need integration by parts twice. So just so you're aware. Okay, so now I've got to do integration by parts again. I'm going to move this over a little bit because I'm running out of room over here. Okay, so I'm going to do integration by parts now. Look, all I'm doing is focusing my attention on the blue box here. Not even that 2, just the blue box. So for that, I'm going to do integration by parts. So I actually, when I start, I get to a point, and I'm not sure, you're probably not there yet, maybe you are. I get to a point in integration by parts where I stop writing u and dv. I just start filling out the box. So like this is x, this is dx, this is cosine x dx, and this up here is sine x. And then I just remember that the formula is ultraviolet is the top 2 multiplied, and then minus the integral of the diagonal. So that becomes x sine x minus integral of just sine x dx. Understand? And the antiderivative of sine x, we know, right, is negative cosine. But then that negative in front of the whole integral is going to make it a plus cosine. And I will have a plus c at this point. But I still need to tack it on up here to this. I need a 2 in front of all this stuff. So I think I'm ready for a final answer here. So we should get negative x squared cosine x plus now the 2 times all this. So 2x sine x plus 2 cosine x plus c. There's our antiderivative. Times pi. Well, this is just the antiderivative of this, right? So now I'm ready to come back over to this now. Okay. Any questions up to this point? So this is equal to pi. And now the antiderivative, which was negative x squared cosine x plus 2x sine x plus 2 cosine x, all of that's the antiderivative, evaluated from 0 to pi. So we're going to need to plug pi into this, right? So we're going to need to know what cosine of pi is and sine of pi. So, and then we're going to have to plug in 0, and hopefully you know what cosine and sine of 0 are. All right, here we go. Let's plug in. So first one, when I plug in first pi, I get negative pi squared. What is cosine of pi? Negative 1 plus, okay, 2 pi, replacing the x with pi. What is sine of pi? 0 plus 2, what is cosine of pi? We just said negative 1, right? Do y'all agree with this? Pi here, pi here, pi here, pi here, pi here. Now I need to subtract from that. I'm going to move this down. So subtract from that pi, and then now plug in 0. Kills off the first 2, doesn't it? 0 into the first 2, they're both dead. 0 plus 0. And then plus, what's cosine of 0? 1, right? So that gives me 2. All right, here we go. We have pi. Let's figure out what's in this parentheses. Negative pi squared times negative 1 gives me pi squared. This guy's gone. And then we have minus 2. And then over here, we have minus 2 pi. The pi hits the 2, so minus 2 pi. And so distribute that pi through, we get pi cubed minus 2 pi minus 2 pi again. Distribute the pi. And that gives us a final answer of pi cubed minus 4 pi. There you go. So if you could take this region and wrap it around the x-axis, right? You would get a solid, and that solid would have a volume of pi cubed minus 4 pi. Pretty cool. Let's check our answer, because I did make up that problem. So let's check our answer. Let's go to Wolfram Alpha. And what I'm going to do here, if it'll let me, why does it take so long now for this? Okay, I'm going to do the integral from, it was from 0 to pi. Will it take that as pi? Pi. Now we have a pi out front of this, right? Pi times, and then it was the integral, it was x squared, right? Times sine x dx. Yep. Pi cubed minus 4 pi, about 18.44. In those units, 18.44, it would be cubic, whatever. It depends on how big this thing is, how we're measuring it. Is that, you know, is it like feet or inches or miles or whatever? So if we rotate it, if it was feet, then it would be cubic feet. Got it? Understand? Pretty cool, huh? All right. Let me see what I've got here, just to give you kind of a quick preview before we shift gears to our next thing here. A quick preview of maybe some old, why is this so slow? See if I've got an old exam here. This would be an exam 3, right? This is pretty new, actually. Just curious what I've asked for on a previous exam. There's an improper integral on here, so I guess they hadn't been tested on that yet. Find the area of the region bounded between these curves. Your graph should be clearly labeled. Write your answer as a decimal. So I actually asked them to get the area of something. Then I said, set up the integrals, but do not evaluate, which give the volume of the solid form by revolving the region bounded by these curves about these axes. There it is, just like I promised. Right? Include any drawings which support your integral formulas. Okay? All right. We're still in this section, okay? By the way, I should mention something. The book, chapter 7, section 2 is washers. Chapter 7, section 3 is shells. I do them together. So there's no homework out of the shells section. So when you're doing the washers homework, if at any point you ever want to use shells, you can. All right. If you want to have additional problems, go do 7.3. Just go look at some problems from 7.3. Those are shell problems. But the way you should be looking at it now is like any volume, any solid of revolution, you have both tools at your disposal. All right. And you just do the one that makes more sense.
Are we gonna have this as a,
I knew you were going to ask that.
if not, then I'll just memorize that.
Yeah, no, this formula sheet, this would be very helpful. This would be extremely helpful. I would have loved to have had this on my test, but I didn't. And so I think that this is too much. I think for learning it, it's good, but I really think it's more important that you understand the geometry happening rather than the formula, which I think you do. And it, once it's kind of like the quadratic formula. Like we all memorize the quadratic formula, right? Well, at some point we memorized it. Maybe you didn't. You know, there are certain formulas you memorize them, right? That will stick, but only for so long. If you could derive it yourself, then you understand it, right?
Yeah.
So like the quadratic formula, obviously I have it memorized, but if I needed to derive it, I could. Like if for some reason I forgot it, I could actually derive it and create it. I think that's kind of what this is all about too. Like, yes, there's a formula, but you could derive it by the geometry if you just understand what you're trying to do by rotating things around. Okay, see how it goes. We still have time before the test, but as of right now, no, I don't intend on that being on there. Okay. All right, so we have done 7.2 and 7.3, but there's one piece of 7.2 that's missing. And it's this little part of the section. And students hate this. I don't know why, it's just, they hate it, all right? So here's what I'm gonna do. I want you to just forget solids of revolution right now, all right? Don't be thinking about we're gonna take a region and rotate it around any axis. Just throw that away. What I want you to be thinking about is the power of the integral. The integral allows us to add up an infinite number of things, right? That's what it's all about. Okay, so I would like for you to just visualize, if you could, a basketball, all right? A ball, any ball, cut in half, all right? Solid. And let's just set it on the table, all right? If I were to describe that to you, all right? If I were to try and describe it to you, I could tell you that I've got this solid laying on a table, all right? The base of the solid is a circle. Okay, so you see the circle on the bottom? Now, if I take a knife and I cut anywhere on that object, So I take it and I cut. If I were to cut it and open it up and look at it from the side, I would see a semicircle, right? A half circle, right? So if I cut it, opened it up, looked at it from the side, that's called a cross section. You should see a semicircle. Everyone see that in their mind? Now, if I cut it at a different place, parallel to the same cut I just made, but if I move a little bit over and cut it again and open it up again, what am I going to see? Semicircle. But will it be the same size as the one that you got from the other cut? No, it depends on where I cut it. So if I cut it right in the middle, open it up, that's the biggest semicircle I'm going to see, right? But if I cut it way out at the edge, I'm going to see a small semicircle. What is dictating how big that circle is going to be? The cut, where I put it, right? But isn't it the ground? Isn't it that circle on the ground that's actually dictating how big that circle is above? The more I go to the edge, the smaller it is. So let me try and start drawing this. All right, so if I were to looking from it from the top, right, then what I would see is basically a circle on the ground, right? That's what I would see. So let me try and draw this now more three-dimensionally. So to draw three-dimensionally, okay, my recommendation to you is to do this. Draw a vertical line and then draw an X that's kind of squashed down. So notice that that looks like this is an X, right? But I didn't draw like that. I kind of squashed it down. That's the best way to try and draw something three-dimensionally on a two-dimensional sheet of paper. So I'm going to transfer that picture of the circle onto that picture three-dimensionally. It would look something like this. Do y'all see it on the ground? Okay, so if I were to take a knife and slice this right here, let's say I slice it from the top, straight right here. That would correspond to this slice right here, wouldn't it? Sort of. And when I open that thing up and look at it from the side, I'm going to see a semicircle, but the radius of that or diameter is based upon that red strip. So that little piece should look like, that's not very good, like that, right? Something like that. Now, if I make a cut, like let's say over here, closer to the center, then over here in this picture, it'd be on this back edge like this, right? And now that cut is going to be, I think I went too big there. It's definitely bigger though, right? Than that other one. Yes? Okay. So now I'm going to describe this object to you in words. I have an object where the base is a circle. And when you take cross sections of this object that are perpendicular to the x-axis, you see semicircles that have a diameter that is the same as the base. I'll say it again. I have an object where the bottom is a circle. See the circle? If you take a cross section perpendicular to the x-axis, okay, if you take a cut, then what you'll be looking at is a semicircle, that's your semicircle right here, whose diameter is equivalent to the base of the object. So as you move left and right, your base changes, and that changes the shape of what's above it. And when you put all that together, you get half a ball, right? Okay. So that's a nice way to describe a ball, right? A ball is just right, okay, half a ball. Okay, so what about this? What if I change something now? I'm going to try and change it. I'm going to describe a different object to you, all right? The object, the base is a circle, all right? A circle of, let's say, radius 1, all right? When you take cross sections of this solid perpendicular to the x-axis, it forms, each cross section forms an equilateral triangle, all right? Where the length of the equilateral triangle is equal to the base. So it's this same object, but instead of a bunch of little semicircles, what is it? A bunch of little triangles. Can you see what that would look like visually? Do you have a mental visual? It's not a ball, right? It's weird though, yes? Okay. What's the volume of it? That's the question. What's the volume of that object that I just described? So I think, I mean, this is where I can bring my visual tools into play here. So let me do that. Where is it? There we go. Why aren't you opening? Oh, it's already open. Let me, there's the code for this one. All right, so unfortunately, I don't have code ready for a circle on the ground. All right, so I have to re-describe this object. This object on the ground is basically the region bounded by two parabolas. So that's the ground. Instead of a circle on the ground, I've got some region bounded by two parabolas. When you do cross sections perpendicular to the x-axis, you get equilateral triangles. I'm going to make this bigger. There's my two parabolas on the ground, right? Okay. Now I'm going to do equilateral triangles. So we're going to have a bunch of little triangles in here. So I'm going to bring a slice in here. All my slices look like this. See all those slices in there? So what does the object look like? Looks like this. It's almost like a little dunce hat or something. I don't know what that is. It's an object, right? And it has a volume. And I want to know what it is. All right. So think about how the integral could work for us here. What? You're adding all the volumes of each of the little slices, right? So if we could just figure out a formula for the volume of one slice, the integral will be able to add them up. Make sense? So we need to figure out what the volume of one of those slices is. All right. I think that went well. Does that make sense visually? Like y'all can get it? Okay. Visual. All right. What if, okay, let me change the shape. What if these aren't equilateral triangles instead? Instead, what if what was above there were squares? So you have a parabola on the ground, you make these slices, and every time you make a slice, you make a square out of it. So the square, how wide it is and tall it is based upon where you are, right? So if you're really close to the edge, you're gonna have a very small square. If you're in the middle, you have a really big square. Make sense? And bring the slice through here. You don't see it? So what would it look like? Look like this. It's not the same as the other one though, right? It's different. It should have a different volume to it. How about this same thing with semicircles? Now, this time the base is not a circle, right? The base is two parabolas. So if I wanted to do that, semicircles, here's what it would look like. Please ignore the bottom part of the circle. I just never fixed the code to take that out of there. So it looks almost like, oh, that's my opacity, right? Little semicircles here. And we create this thing that kind of, I don't know what that looks like. It's not quite half a ball, right? Or because the bottom is not circular. If the bottom was circular, then this would be half of a ball. Half an onion, yeah. Half an onion, yeah. I like that. Okay. So these are called volumes of perpendicular cross sections. right? We're trying to find the volume of something where we know something about the base and we know something about the perpendicular cross sections. If we know that, then we can figure out volumes. All right, so we ready to do an example? Ready or not? Where's my? Yeah, I'm just going to make one up. The base of a solid is the region bounded by y equals 1 minus x squared and y equals x. Cross sections perpendicular to the x-axis form squares. Find the volume of the solid.
Cross sections related to the z-axis.
No, well, your knife is coming in from the z-axis if you want, but when it cuts, we want to make sure that our knife is perpendicular to the x-axis on the ground. Let's draw it, and I think it'll make a little more sense.
Well, perpendicular to the x-axis is also just partial. They're parallel to the y-axis.
Yeah, parallel to the y. You could say that. Either way, I could have said either way. Okay, so what I'm going to start with is drawing the base of the region. The base of the region is, or sorry, the base of the solid. The base of the solid is the region bounded by those two curves. So I've got to draw those two. That should be a pretty quick sketch because we are familiar, hopefully, with what those look like, right? Y equals 1 minus x squared should be a parabola that opens down. And y equals x should be the identity like this. And is it clear what the region bounded by those two is? So this is the bottom of this solid. And if we come in here from the top and we cut straight down, we could cut, any way we want. We could cut it this way or that way or this way or that way. There's all these different ways we could cut it, right? But just to be sure you understand what's going on here, I have to tell you that if you take a cut perpendicular to the x-axis, that means a cut here, or a cut here, or a cut here. As long as your cut is perpendicular to the x-axis, that cross section that you get when you peel it, open it up, should form a square. All right. If we change the problem and I said perpendicular to the y-axis, then you would have to imagine that your cuts are coming this way and forming a square. That would be a different object. It would have a different volume. All right. So what I like to do right now at this point is I like to try and draw this region in three-dimensional space. And it's never too early to try and draw in 3D. So it's like the x-axis is on the ground, the y-axis over here like that. And you just kind of do your best, all right? I mean, it doesn't have to be perfect. try and draw like what your diagonal would look like through there. And then what your parabola might look like. Look, I realize that that looks pretty damn good. Okay, and I've been doing this for a while. I mean, it's not terrible, right? It looks good, right? So, I mean, this is like a lot of years of doing this. So, I mean, I understand yours may not look that good. The important thing is to understand that your region on the ground, you know where I actually learned the most about drawing 3D is I took a drafting class in high school. And I think when I was in that drafting class, we had just got this revolutionary software called CAD. It had just come out, CAD, and we were using CAD to do things, but everything else we did by hand. And so we would draw things in perspective and stuff. So I really was forced to do, have y'all ever heard of, I think it's called 3-point perspective. If you have a solid object, you look at it from like front, side, top, and you put all 3 drawings on one page. We used to have to do 3-point perspective with by hand. Isometrics, yeah. 3 different, yeah. So yeah, I mean, that helped a lot because you would have to draw things that were skewed like this. Okay, all right, so there it is. There's my drawing, right? So now I'm going to come in through with my slice. Here's my slice. I'm going to do it in black. I'm going to slice right here, okay? Now, when I slice, I want y'all to think about that slice almost like a rectangle. Like we've been doing rectangles, right? I'm going to take this little infinitesimally thin slice of this thing. It is perpendicular to the x-axis. Over in my picture, that's here, isn't it? Now, that is supposed to come up and form a square. So from this, it comes up, over, and down, and forms a little square over here, right? I'm going to zoom in on that square. If I could just find a formula for the volume of that one little square, right? If I could find a formula for just the volume of that little sliver, then I could integrate from the left endpoint to the right endpoint and add all those up, right? All infinitely many of them. Well, do you know how thick that little slice is? dx, right? Hasn't the width of the rectangle always been dx for us here? So this is dx, that's good. Okay, this is the tricky part, if there is a tricky part, other than the drawing. Do we know how long this side is here? It's the difference of the top function and bottom function, right? Right, isn't it? It's, look, this, I don't know how to highlight this anymore. The blue here, see this? I'm right here, I'm looking back here. The top edge of this rectangle is always dictated by the blue, and the bottom edge is always dictated by the red. As I slide it left and right, the blue and the red are changing. So the distance between these should be that blue function minus the red function. So this should be the blue function. What's the blue function? 1 minus x squared. But then I want to take away from that what? The red function, which is x. 1 minus x squared minus x. But it's a square. So the height of it is also the same thing, right? The height is also 1 minus x squared minus x. And so if we have a little box here and I know the length, the width, and the height, the volume is just all 3 multiplied together. We're going to do a triangle next. And then you'll see what we'll have to do, right? And then we'll do a circle or semicircle, and all of them are going to have different formulas. I started with the easiest one because it's a square. Okay, so do we all agree then that the volume of this little slice, just the little slice, should be length times width times height? So it should be 1 minus 1 minus x squared minus x times itself again, so squared, dx. dx is the thickness. Okay, that's the volume of one slice. Let's add them all up. Integral, right? So we bring in the integral. We're going to do the integral of 1 minus x squared minus x, all of that squared dx. What am I missing? What's the only thing I need? Limits of integration, right? I need to know where to start and stop this slicing, which means I need to know where these two things hit each other, which means I need to set them equal to one another and solve. So for the intersections, or the intersection points, I set 1 minus x squared equal to x. I'll move everything to the right side. And unfortunately, that does not factor. I made this problem up on the fly. So that means you'd have to use quadratic formula to solve that, which, we're Cal 2 students, so we should be able to do that. X is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, which equals negative 1 plus or minus the square root of 5 over 2. And that gives us two answers, right? One of these is positive, the other one is negative. Now we could get these as decimals, but I'm going to leave them as exact answers. So I think I'm ready. My integral is going to go from negative 1 minus root 5 over 2 to minus 1 plus root 5 over 2. Right? Those are my two x-intercepts. The one on the bottom is negative. The one on the top is positive. And then it's going to be, well, I guess I could have cleaned this up a long time ago, right? I mean, this right here, I could have just dropped the parentheses out and just did 1 minus x squared plus, 1 minus x squared minus x. It doesn't matter how you write it. I'll leave it. 1 minus x squared minus x squared dx. There it is. We're not going to evaluate it. We're just going to set it up. Do y'all agree that this integration would be easy? Like if you distributed, if you cleared all this out, right? Just drop the parentheses, put these together, and then square the whole thing, just multiply times itself, you would get a polynomial. You can integrate that term by term. Now plugging in these numbers would suck, but we could do it, right? And a computer could do this easily for us. So yeah. Yeah, everything is based upon what that shape is that the cross sections form. Let's do triangle. Triangle gets a little tricky. Triangle gets a little tricky. All right, so can we do the same problem? Any questions at home? I'm changing one thing here. Squares, I'm going to go to equilateral triangles. Equilateral, I want to put two L's. Yeah, two L's, equilateral triangles. Same exact region on the ground. Cross sections are perpendicular to the x-axis. The only difference is when you look at it from the side, it forms an equilateral triangle instead of a square, which means that my whole picture is almost the same, right? So I get to copy and paste it. I do, you don't get to. But because of time, I only have a few more minutes. So the only difference I'm going to have here is over here in this picture. Don't think I'm going to be able to get rid of that. Yeah. Really? Yeah, that'll work. So here's my here's my region on the ground. And then my base is still this little rectangle on the ground, right? But now when I look above it, it's going to form an equilateral triangle. Equilateral means all sides the same, right? All sides the same length. So let me zoom back out and see all the imperfections in my graph when I'm zoomed in like that. Okay, so let me just zoom in on that. I've got this equilateral triangle, which has some thickness to it, right? It would be nice if I had a formula for the volume of this. One thing I do know is how thick it is. And if I know how thick it is, then the only thing really left for me to resolve is what the area of that triangle is. If I can find the area and then multiply it times the thickness, I'll have the volume. So what is the area of that triangle? Well, what do we know about it? What's the one thing we know about this triangle? The side, right? The base is, well, we just did this on the previous problem, right? So this is 1 minus x squared minus x, right? That's what that base is. So the area of a triangle is 1/2 base times height, right? You don't have the height. You don't have the height. The height would be this distance from here to here, right? That would be the height. Now, there is a way to algebraically figure out what that height is. Don't go down that road, though, okay? I want to remind you of something from pre-cal that hopefully your pre-cal instructor told you. If you had me, I did, and if you've forgotten, that's your fault. So this is something from pre-cal. If you have a triangle, not a right triangle, just an arbitrary triangle, where this side is B, base, and this right here from here down is H, we all know, someone told us that the area is 1/2 base times height. Y'all know why it's this way? You do? Yeah? Why is that true? I mean, there's a real easy way to show it.
Half a rectangle.
Yeah, take that same picture, make a copy of it, rotate it. Got to rotate it again. Rotate it like this and put it like this, okay? So I've made 2 copies of that triangle, rotate it and put it there. And then take this right here, cut it off and stick it right there. Now you've got this, right? Now you've got a rectangle. What's the area of this rectangle? Well, it's this base times this height. So the base times height is the area of 2 of those things. Remember, I did a duplicate copy. So I just half that, and that's the area of the triangle. All right, that's not what we're here to talk about, though. Just want to make sure everyone's comfortable with just the idea that the area of that is 1/2 base times height. Okay, so there's another formula in pre-cal that says that the area is also equal to 1/2 A times B times sine of theta. Now, B is still B, all right? Theta is this angle, and A is this side. So what this formula is saying is that if you know 2 sides of a triangle, and you know the angle between those 2 sides, you can find the area. All you need is 2 sides and the angle between them, and there's a formula for the area. Now, this formula actually might seem very crazy, but it's so simple to show you where it comes from. All right. All I have to do is ask you, if you look at this right triangle right here, see that right triangle in yellow? If I ask you to look at that and you tell me what sine of theta is, what would you tell me? Sine is opposite over hypotenuse. So what would it be? H over A, right? Okay, solve for H. So get rid of the A, multiply both sides by A. And you get H is A sine theta, right? Okay, now go to this formula and replace H with A sine theta. And you get A sine theta times B half, right? So it's a very simple thing to show. But a lot of students aren't either aren't given that formula, or maybe, I don't know. What happens a lot in algebra, and this is just the truth, is that a lot of times there's so many college algebra teachers, not all of them will teach like more math, right? So they don't really remember the types of things that you need later, right? So that certain things aren't emphasized. This is absolutely emphasized because I need that in calculus. It makes life a lot easier. Why does it make it easy for us here? It's equilateral, which means all the angles are what? 60 degrees. So I have the angle between all of those, right? This is 60 degrees here, 60 and 60. And then you know two of the sides, you know all three sides, in fact, right? So, but you definitely have two sides in the angle between them. Make sense? So the area of, well, let's just do the volume. The volume then would be 1/2 A times B, that's this side times itself. So that's the same thing from earlier, 1 minus x squared minus x times itself, and then sine of 60 degrees. What's sine of 60 degrees? √3/2. √3/2. And so if I take that and multiply the half out front, I get a final formula for the volume, which will be √3/4. And then 1 minus x squared minus x, that entire quantity squared. Any questions on that? Now, that's not my final answer, right? I've got to do the integral now. The integral? Yeah. I'll squeeze it in here. Well, wait a minute. Hold on. That's really close to the previous answer, isn't it? Look at the answer. Look at this. Yeah, the only difference is a constant, isn't it? Isn't our answer this, basically this?
I think that goes for any shape.
Pardon me?
I think that goes for any shape. It's just a different constant.
Not for a semicircle.
Uh,
A semicircle, you're going to have a pi in there because the area is going to have a pi r squared somehow.
oh, okay.
So yeah, not everyone. So it's
All right.
this same answer, but we have √3/4 in front. It's just because a triangle and a square are very like intimately connected to one another. Okay, so let's do this. Why don't I offer you as a quiz, all right, just something you can turn in for you to do the same problem where the cross sections are semicircles. See if you can do that, all right? Figure out, which basically just means, can you find a formula for that little slice? All right. I will send out an email link for you to upload that to me. Let's say that'll be due by next time we meet. Oh, wait, that's Thursday, right? Oh, wait, let's do it. Monday, let's say Monday, yeah. Sound fair? So what I would expect for you to do now is your homework for 7.2. It has a few of these in it. And then, you know, if you want to venture out into 7.3 to do some more, you can do that. What's coming next is we need to do arc length and surface area. And then before you know it, we're going to be in chapter 8. While I was doing that, I know if you need to go, you can. When I did the equilateral triangle, no one bothered to challenge me here that these angles were 60, 60, 60. Why is that 60, 60, 60? The sum of the angles of a triangle have to be 180, right? Does that hold for all triangles? Yes? Yes. Yes. Triangles on a flat sheet of paper in two-dimensional space, yes. Okay, but it doesn't hold all the time. All right, so I'll give you an example. There's something which you will study later if you continue on. I don't know, it depends on your field. Engineers probably will. It's called spherical geometry. So just think about a sphere, right? A sphere. Imagine that I were to take a point at the North Pole, and then I were to travel along the sphere down to the equator, and then move along the equator to another point, and then travel back up to the North Pole. That is a triangle on a sphere. So on a sphere, that's what a triangle looks like. But if you look at this right here, think about like tangent lines. If you have a tangent going this way and a tangent going this way, what would the angle between those two be? 90 degrees. And then if we do the same thing here, like a tangent line, that angle would be 90. You're already at 180. And you have another angle up here that you haven't even talked about. So the sum of the angles in that triangle are not 180. So it gets weird because depending on in spherical geometry, those rules don't apply. A flat sheet of paper, that's called Euclidean geometry. So there's all these different geometries. Do you think spherical geometry is useful? We live on a sphere. Yeah, it is useful. So you have different rules in different spaces. There's another one, parallel lines. Do parallel lines ever intersect? Not in Euclidean geometry, right? But in what's called perspective geometry, they do, all right? So you can go, you're not gonna hurt my feelings. Don't go. So like if you're drawing a street and some buildings on the side, right, on a flat sheet of paper, you can see that all my lines that are parallel would never hit each other, right? But if I try and draw this in a different geometry system, I can draw it like this. And that's a better picture of a street with two buildings on the side, right? That tricks your eyeballs into thinking it's three-dimensional when it's not. Okay, that's called perspective geometry. And in perspective geometry, all parallel lines must intersect at some point way off in the distance called the vanishing point. If you've done any drawing before art classes, there's some point way out here called the vanishing point where all parallel lines must go to it.
So is perspective geometry only important for artistic rendering?
No, absolutely not. Absolutely not. Perspective geometry, the thing that I found amazing as a student is that we're born and raised basically in Euclidean geometry, right? Everything we do is Euclidean. The X, Y, flat sheet of paper, parallel lines don't hit each other. Sum of the angles of a triangle is 180. All that's Euclidean. Well, Euclidean is just one little branch of geometry. There's non-Euclidean geometry. There's stuff that's not. Perspective is one. Spherical is another. Cylindrical coordinates. There's all these different systems. Special relativity, Einstein, that's a non-Euclidean geometry. It is something that does not behave the way things are behaving in Euclidean. So yeah, it becomes very applicable. Other than art, it does.
Like how people can like determine distances and stuff just from like photos, if that makes sense.
Sure, absolutely. Yeah, you can basically convert something that's in perspective to Euclidean, right? And you go back and forth between the two geometries. I don't know if you know this, but if you ever try and draw something three-dimensionally and to trick your eyeball on a flat sheet of paper, like let's say I want to draw a shoebox. Right there, like that looks like a pretty decent little shoebox, right? Or a box. In reality, though, if I put a box out here on this table, it would not look like that to my eye. It would not, all right? I have to draw it a certain way for it to work. What I have to do is I actually have to pick three vanishing points. 1, 2, 3. Okay, then I draw my box. So I'll start with one corner of the box. I'm going to draw these lines to here. Okay, so now I'm going to draw another line here. This is part of my box. I'm going to draw this back like that. Let me draw another line to my box. Now from there, I've got to go towards this one. Just let me draw and then you'll see it in the end. So I draw here. Let me see here, there. This one would have to go back towards that one. Then here, then this one would have to cut back down like that. Oh, sorry, no, this one goes like this. So I'm gonna have to cut down and then like that. So there it is. The thing in black is a true, drawn in true perspective. And when you look at that, you're like, that's not what a freaking box would look like in real life. Well, here's the trick. Each one of these points, right? You could draw a circle through that point, right? Through those 2 points. Then you could draw a circle through, circle through these points and circle through these points. Imagine that those are bubbles sitting on top of the page. Okay, bubbles sitting up above, semicircles. Those 3 bubbles hit at a point. If you could put your eye right where that is, it would look perfect. It would look perfect, which is why when you go to an art gallery, they usually have a place to stand and look at the art. They're trying to get your eye in that perfect position so that it looks exactly the way the artist intended it to look. It's done especially for things that are drawn that are supposed to look 3-dimensional. They try and get you to where those 3 bubbles hit each other. And it's like, if you're right there, now it would look exactly the way it looked if you were actually standing there. Maybe it's like a scene of a street or something. So it's very, you know, you kind of like, whoa, when you start to realize Euclidean's not the only thing out there. It's kind of mind-blowing. All right, gots to go.
Wait, I have a question.
Yes.
You said you were doing a quiz, right?
Yes, the quiz is, yes. The quiz is for you to do this same problem we did here. But instead of, we've done squares, we did equilateral triangles, do semicircles.
I'm gonna have to take a picture. I didn't write
Okay,
all
there
that
you go. I'll
down.
leave it up there for you.
I just did the work.
You need the what?
What?
Okay, I thought you were asking me a question.
No, I got it.